Welcome to Unit 7, Inference for Quantitative Data with an emphasis on means and AP Statistics. In this video, we're going to discuss topic 7.2, constructing a confidence interval for a population mean. Alright, consider the following questions. What is the mean length in inches of all adult largemouth bass in Lake Erie? What is the mean amount of time name brand AAA batteries last? What is the mean systolic blood pressure for a teenage male athlete in a seated position? These are three great questions that all seek to find the mean of a population. But, as we discussed previously, finding the mean of a population is really hard. How am I going to find the mean length of all largemouth bass in Lake Erie? I'd have to catch them all, measure them all, add them all together, divide by how many I measured to get the mean. It's never going to happen. There's probably millions upon millions of AAA batteries out there. I can't test them all to see how long they last. And there are millions of teenage male athletes, so I don't know if I can get all of them to measure their blood pressures. So to answer these questions, basically it's near impossible for us to find the true population parameter. The true population parameter is mu, and I really wish I could find it, but it's probably never going to happen. However, I can select a sample from that population, and I can find the mean of that sample. That's called x bar. This is a sample mean, and I can use this statistic to point me to maybe what that true mean could be. That's why we call the mean of a sample being used to estimate a true population mean a point estimate. However, by now you should know that samples vary. Yes, I can go and get a sample of largemouth bass fish from Lake Erie, and I can get another sample, right? There's millions probably of different samples out there, all of a certain size. And the one thing I know is true is that they're all going to vary a little bit. So the mean of our sample is one of many possible sample means out there. This is why I need to consider sampling distribution first and foremost, because the whole point of what we learned in Unit 5 about sampling distributions is that they show us what all possible sample means will look like. So let's talk about a sampling distribution for a sample mean real quick. All right. Well, we already know that the mean, the center of the sampling distribution, which is, this actually should make complete sense. It's literally a mean of means. It's a mean of a bunch of x bars. And we know that if you think about that, we just got done saying that means are going to vary. Some samples could be a little higher than the truth. Some samples could be a little lower than the truth. But the mean of all those samples should be equal to the true population mean right smack dab in the middle. But we also know that samples are going to vary, just like population varies, right? So the standard deviation of a population is just sigma. This tells me how any one fish in the large population varies from the mean. But now we're talking about a sampling distribution, which doesn't talk about one fish. It talks about a sample of fishes. So the standard deviation of a sample mean is going to take that standard deviation for any one fish in the population and divide it by the square root of your sample size. Because of course we learned that bigger samples vary less. So a sample of 55 fish should be much closer to the truth than, say, a sample of one fish. So that's the standard deviation formula, which will tell us how far we can go up for 1, 2, and 3 standard deviations, down 1, down 2, down 3. Now, notice that the picture here is normal. Well, of course, we do have to make sure our conditions are true, right? The center is only going to be the true mean if our samples are random to avoid bias. I'm only allowed to calculate the standard deviation of a sampling distribution if I have independence. So I do have to make sure that my sample size is under 10% of the population to assume independence. And the normal model can only be used if I'm big enough. Well, how do we know we're big enough? Well, what's different than proportions that we learned last unit is there's no such thing as successes and failures when you're working with quantitative data. So we actually kind of have two things here. One, if the population is told to you to be normal, like if we know that the length of largemouth bass fish in Lake Erie is already normal, then any sample size will produce a sampling distribution that's normal. Otherwise, we will need the central limit theorem, which tells us, hey, actually it doesn't even matter what the population looks like. All sampling distributions will still be normal as long as your sample size is 30 or larger. All right, so this is all great and fine, but remember, we don't know the true mean, nor do we know the true standard deviation, because those would involve us having to analyze the entire population of all largemouth bass fish, and that's just not really possible. So let's actually backtrack for a second. Let's just pretend for a second that we do know the mean length of all largemouth bass in Lake Erie. and the standard deviation as well. So let's just say somebody was able to measure them all. They could take all those values, maybe plug them into their calculator, right? They could take every fish. Think about that, right? Every single fish. They could plug it into list 2 on their calculator. That's going to be extremely long. There's probably hundreds of thousands of largemouth bass fish in Lake Erie. And then, they could do a stat, slide over to one variable stats, and they could calculate the mean and the standard deviation of the population. Obviously, that's impossible to do, but let's pretend for a second that we could. All right, so we know that the mean and the standard deviation of all largemouth bass fish in Lake Erie is 13.2 inches with a standard deviation of 0.75. Okay, what does that mean? It means that the average of all the fish is 13.2 inches and that any one fish on average will be about 0.75 inches from the mean. Okay, great. Then we could start thinking about samples of size, right? So let's think about samples of size 40. Okay, so if I were to take out 40 fish from Lake Erie in a sample, which would be very easy for me to actually do and get a mean of, and okay, but remember, sampling distribution shows all possible samples. So the idea is if I think about all possible samples of size 40, the mean of all the possible means, well, that would be the truth, 13.2, right smack down in the middle. Some samples are going to come back a little higher than that, duh. Some samples are going to come back a little bit lower than that. So obviously we get the 13.2 in the center. But then we have to understand that the standard deviation of our sampling distribution is going to change as well. The 0.75 is for any one fish, but we're now talking about 40 fish. And the mean of 40 fish is going to be much closer to the truth than any one fish. So that's why the standard deviation shrinks. So we're going to take the 0.75 divided by the square root of 40, we get 0.1186, and that tells me how much I go up, 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 and how much I go down, down, down. Okay, this is great. This is awesome. But again, I'm assuming that I know these true values. You know what? We already learned all this back in Unit 5. But here's the idea, guys. We know that if I'm going to go and get a sample tomorrow I'm going to go get a sample. Well, if I said today, where do I think that, where do I think that that sample is going to fall? Well, it would be pretty weird for that sample to fall up here. Be pretty weird for that sample to fall down here. You know what? I'm actually pretty confident that my sample's probably going to fall somewhere in the middle. Why do I feel that way? Because that's where the large majority of samples are. So now let's think about this. Let's go in blind. Let's go in blind, right? To be honest, we don't know the true mean of the fish. We don't. So let's just go in blind. Let's pretend we don't know. Let's pretend we don't know any of those numbers on the bottom that we labeled. Because in reality, we don't. But let's see here. We do know that the sampling distribution still exists. Even though I can't make it, it still exists. It's still out there. Somewhere out there is the truth. I just don't know it. So when we think about that sampling distribution, we know that, again, 2.5% of sample means would be really, really weirdly low. 2.5% of sample means would be pretty high. But most sample means 95% are in the middle. So that's, again, if I'm going in blind and I don't know what the truth is, all I have is my sample, I'm very confident that my sample is going to fall somewhere in the middle. So this goes back to the idea of a confidence interval, right? I don't know where my sample is, but let's just say that my sample falls right here. Well, if I build an interval around my mean, my sample mean, look, the truth is going to be caught. Or even if my sample is kind of down here somewhere, but still in that middle 95%, when I build an interval, the truth gets caught. So the point is if I'm going in blind, meaning I don't know any of those numbers on the bottom because I don't know the true mean or standard deviation of the population, well then I'm just going to have to go in on the assumption that if I get one sample out, it's probably going to be in the middle, which means if I wrap an interval around it, I'm probably going to catch the truth. So again, this is where we come up with our confidence interval formula. This is a very similar concept that we saw with proportions. So I'm going to start with my sample mean, x bar. I'm going to go up and I'm going to go down by this back part, which is called the margin of error. Now, to calculate the margin of error, first I have to think about how confident we want to be. If I want to be 95% confident, everybody knows that that's the z star of 1.96. Hope you know that by now. And then I'm going to go up and down by the standard deviation, sigma divided by the square root of 1, which we already showed was 0.1186. So again, let me just do one more example. If my sample comes back right around here, once I go up and once I go down by my margin of error, I have a lot of confidence I will capture the truth. In fact, any sample within that middle 95%, any sample will produce an interval that catches the true mean in the middle. The only way a sample will not capture that truth is if it's way out here. If I have one of these really, really low samples, maybe when I build my interval, oh no, I missed the truth. But remember, I don't really think samples like that are going to happen. I'm going to bet my money that most samples, including mine, are going to be in the middle somewhere. So then all we got to do is take our sample mean, whatever that ends up being, go up and down by the margin of error that I calculated here. So we call this a one sample z interval for a population mean, right? Seems pretty easy. All you're going to do is take your sample, your mean, and then you're going to go up and down by the margin of error. Seems really, really easy. Well, if it was that easy, the video would be ending right here, but it's not. Because there's one giant hiccup, and I hope maybe on your own you caught this. The formula for the standard deviation right here requires that I know the true standard deviation of the population, which if we're going in blind, we don't know mu. Why would we know the standard deviation? I mean, the standard deviation tells you how far one fish is from the mean of all fish. Why would I know the standard deviation but not know the mean? That just seems silly. So the problem is that I can't use this. I can't. It seems so easy, but I really want to. But the problem is that standard deviation is unknown. So what the heck do I do? Because remember, I'm going in blind. I don't know the mean. And if I don't know the mean, then there's no way I know the standard deviation. So what do? Well, we've got to work with what we got. And believe it or not, we've actually seen this concept before. Well, what we're going to do is we do know the standard deviation of our sample, right? So we know the mean, right? That's pretty easy. Calculator could get that for you. Type in your 40 lengths into your calculator and you can get the mean. But you know what your calculator can also give you is S, the sample standard deviation. That says how far any one fish in your sample deviates from the mean. Okay, so we've actually done this before. Since we don't know the standard deviation of the population, we could replace it with the standard deviation of our sample. Now the only change is that we have to call this standard error instead of standard deviation. So far this seems like a great fix. In fact, it's very similar to what we did with proportions last unit. So we kind of fixed that problem. And to be honest, the S is not going to necessarily be equal to the standard deviation of the population, but it's actually close enough that we should be okay to get a pretty accurate answer here. But remember, it's the twin brother. I'm using the exact same formula. All I'm doing is replacing sigma with S, the standard deviation of my sample. Okay, obviously this has a new name called standard error, and pretty simple, right? All we're doing is replacing sigma with S, the standard deviation of our sample. Now, just real quick, we want to make sure we understand what does this value describe. This number simply describes how far a sample mean will typically be from the population mean in repeated samples taken from the same population. Go back to the very beginning of the year when we talked about what standard deviation is of a population. It's how far a typical value is from the mean. So here in a sampling distribution, we're no longer talking about a value. We're talking about a sample mean, right? The mean of a sample. So this is how far a sample mean will typically be from the population mean. And bigger samples should produce means that are closer. That's why when you divide by the square root of n, your standard error is going to shrink. Okay, this is all great. This is all awesome. But this actually brings up a new problem. Because we're replacing sigma with S, there's a problem. Now, I'll be honest with you. This is a little bit of a story, but it's worth hearing. Years ago, and I mean years ago, they didn't do anything about it. They still used the normal model, right? They still said, okay, we're gonna take the mean, we're gonna go up, we're gonna go down, we're gonna do a z star, and instead of using standard deviation, we're gonna take the standard deviation of our sample, divided by the square root of n using standard error, and that's how they built the means. But what was actually found out was by a guy named William Gosset. He found out that when you have to replace sigma, the standard deviation of your population, with S, the normal model just wasn't as accurate, right? Remember what's going on here. We don't know the middle, right? So we already don't understand what the middle is because that's the true mean that we don't know. And then now we don't even know how much to go up or down. We're actually just kind of estimating it. We want to use sigma divided by the square root of n for that sampling distribution, but now we have to use S divided by the square root of n. So now how much we go up and how much we go down is actually off a little bit. So the problem was that the normal model actually isn't quite accurate enough. And this guy, William Gosset, this famous statistician, kind of realized that. He realized that it wasn't accurate enough. So he set out to create a whole new model. And the whole point is that he wanted a model that is better than the normal model in the situation where you have to replace sigma with your standard deviation of your sample S. So he actually did this. He created this model. It was amazing, and he called it the T model, okay? Now, here's the idea, was that his T model was better. Now, let me talk real quick about the T model, because I don't want this to be like a brand new model that, it's going to spend weeks for us to understand. It's very simple. Imagine if we were to take the normal model and sat on top of it. What would happen is the middle would flatten out, it would squeeze down, and that would cause the tails to kind of flare up. So a T model, and again, my drawing skills are terrible, but a T model is really very similar to a normal model. It's still symmetric. It's still got a tail to the left. It's still got a tail to the right, but it's flatter, meaning that those tails are wider. So, we still have the mean in the middle, but because our standard error is not as accurate, we need to go out a little bit more. So, what we usually said, 3 standard deviations is so crazy high or so crazy low. No, it might not be so crazy because those tails are a little bit wider, a little bit more full. So the other thing that William Gosset realized is that, one T model wasn't good enough. He actually created tons of T models, each one specific to the sample size. Because what he found out was that for really small samples, the standard error was even more inaccurate, so he had to make those models even flatter and more spread out. But for larger sample sizes, the T model was, actually fairly close to normal, so it wasn't as bad. So, I know this seems a little bit confusing, but the good news is that all T models are very similar to the normal model. They're just a little flatter and more spread out. In fact, the larger your sample size, the more and more the T model will look like. Let me kind of give you a little bit of an explanation on this. Sorry here, I don't know, my PowerPoint got messed up there. There we go, okay. So there's only one normal model out there. There's only one. We all know it very well, right? We all know the normal model. We know that when you have a normal model, you can find z-scores. All you got to do is take your sample minus the mean divided by the standard deviation, which is sigma divided by the square root of n, right? Because we know mu's in the middle, the true mean's in the middle, and we know the standard deviation is sigma divided by the square root of n. But, remember the problem we have here is A, we're replacing sigma with S, and furthermore, we don't even know what the true mean is. So there is only one normal model out there, but when the big idea, and this is what I'm actually trying to say as many times as I can, is that when you replace sigma with S, the normal model, it just doesn't become as accurate as we would wish. So these are the T models. The idea is that the T models are just specific based on your sample size. If you have a very small sample size, like maybe you only look at 4 fish, you're going to be very, very flat and very, very spread out. So there's a T model for that. Then if you have a sample size of, let's say 30, right, then you're actually going to be, even more normal. Now, oh man, my pictures are bad, but you get the idea, right? It's still going to be a little flatter, a little bit more spread out, but not as bad. And actually, when we get into really big samples, like maybe a sample size of 500, to be honest, it's very normal, right? And again, what I want you to understand is all of these look normal. It's just a matter of how flat they are. And that's kind of the idea, is that he was realizing that, n plays a big part in the spread, right? I mean, look at that. The standard error needs n, and that is why smaller samples are a little bit more spread out, hence flatter, more spread out. Bigger samples, not so much. Now, we did not have this problem with proportions because there was no sigma with proportions, right? Here there is. So I hope you guys are understanding this. There are actually tons and tons. I only drew 3. There's tons and tons of T models, and he made a T model for every single sample size. Now, how did he define these different T models? Because, there's only one normal model. So when you say normal model, you're only talking about one. But when you're talking about a T model, oh boy, there's a T model for a sample size of 4, sample size of 30, sample size of 500, sample size of 41, sample size of 32. There's different T model for every sample size. So, if it was up to me, I would have named each model after its sample size, but he didn't. He was, I don't know why. I'm sure there's a great reason why you can find out, but he named each model after its degrees of freedom. So to specify which of the many T models that you're going to need, he used degrees of freedom. All right. Don't let this be weird, even though I know it sounds really weird. It's a really, I think it's kind of a cool name, degrees of freedom. But remember, all a degree of freedom is, and we just use DF for degrees of freedom, it's just your sample size minus 1. That's all it is. It's your sample size minus 1. This is just how William Gosset defined his samples. So if I were to look at this first model I drew, I would say, oh, this is a t-model with 3 degrees of freedom. Force in your sample size. Oh, this is a degree of freedom of 29 degrees of freedom for this model. Oh, this one has 499 degrees of freedom. And what we found out was that the more degrees of freedom you have, the bigger your sample size is, the more the t-models really kind of morph into the normal model. And I have this graph to kind of show you this, right? And this is kind of interesting. And I really want you to realize how much these t-models really do look normal. They have the same characteristics. They're just a little flatter and more spread out on the tails. So for example, if you have a sample size of only 2, very small sample size, 1 degree of freedom, that's this blue line right here. Notice that it's actually maybe not as dramatically flat as I kind of made it out to be, but it is. It's a little flatter and a little bit more spread out in the tail. So look down here at the tails, they're a little bit higher, which means wider than other samples. Now the normal model is this powder blue one right here at the very, very top. And then again, notice how as our sample size increases, meaning the degrees of freedom increase, that the models actually become more and more normal. For example, with a sample size of 6, which really isn't very big, 5 degrees of freedom, that's the red model. And my goodness, it almost, not quite, but it almost fits the normal model very, very well. It's not that far off. But again, the whole point was that William Gosset was finding out that even when it's a little bit far off, it was leading to inconsistencies in his data. That's why he created the t-models, because even though they weren't that much different than the normal model, they were way more accurate in doing his work. All right, and again, we can even go up to 30 here, right? So 30 degrees of freedom would be a sample size of 31. And look how close, that's the purple. You can almost barely see the purple because it's almost directly on top of or underneath the normal model. And that's not really a huge sample, but it is, right? It's good enough to be very close to normal model. So these are the t-models, okay? So I know that this seems a little bit confusing, but the good news is they're very much like the normal model. And the only other thing I want to mention is that, when you're using a t-model, check this out. We're going to use what's called a t-score. And how do you find a t-score? Well, you take your sample mean minus, the true mean, and you divide by the S divided by the square root of n. Because when you have to replace sigma with S, that's when you use the t-model. So an actually t-score is just the same as a z-score, except it's that denominator that's really different, right? We're using S in place of sigma. That's the whole reason why William Gosset invented the t-score. So just to give you a quick background, it's called a t-model. Where he came up with that was that, when he found all this, he was working for a company, and his company really didn't want him to share this information because this was, in the statistics world, this new model was like, oh my gosh, a brand new model, this is crazy. It's more accurate. And his employer really didn't want him to share that information. But he thought that it was pretty important that everybody in the world, in the stats world, knew this information about this new model that he was showing was more accurate when you replace sigma with S. So he published his reports, he published his new models under a pseudonym called Student T. Now, I kind of would have came up with a cooler name than that, but he called himself Student T. That way he could publish his results and pretend that it wasn't him, and that's why it became known as the T model. Okay, let's circle back. All right, so we have our sample mean, and we have our sample standard deviation. What we want to find is the population mean. Let's not lose sight of what we're trying to do here. We're trying to use a sample mean to point us towards a population mean. Okay? Now, we can't define the sampling distribution because we don't know sigma, we don't know mu, but we can certainly envision it, like it does exist. Okay? But the sampling distribution that we want to envision is not necessarily going to follow the normal model when we use standard error, but it will follow the T model. So, this is really essentially pretty easy. Here it is. Okay. This is called a one sample T interval for a population mean. So when we're using a sample mean and a sample standard deviation, we want to understand, hey, 95% confident, right? We want to think about that sampling distribution that has 2.5 at the bottom, 2.5 at the top, and 95% in the middle. And that's where we really hope our sample falls. That way, when we build our interval, we capture the truth. So even if our sample is a little bit higher, when we build that interval, the truth in the middle is captured. Okay, great. Very simple. So we're going to take our sample mean, x bar. We're going to go up, we're going to go down by our margin of error. But wait a minute, this is a T model. So no more Z stars. We're now going to use T star times the standard error, which is S divided by the square root of n. So this is what happens. Because we're using S in place of sigma, we have to use a T model. A T model is very much like a normal model, a little flatter, a little bit more spread out. Boom, that's it. It's really that simple. all right, you're going to be able to calculate this number. Remember, you could type all of your fish into your calculator and get the sample mean. You're going to be able to calculate this number. Your calculator could do it for you. Again, once you type all that data in, calculator's going to give you the mean and the standard deviation. The only other thing we really need in this formula is the t-star. Well, guess what? You probably never realized this yet, but if you go second vars on your calculator, look right underneath invert norm, there's invert t. All right, when you select invert t, it's going to ask you for two things. First, it asks for the area. That's the same area that invert norm was asking us about. So if we want to be 95% confident, that we'll put 0.025 at the bottom. So we're going to type in 0.025. That's the bottom 2.5% that the calculator needs to know. And then we're also going to put in the degrees of freedom. So again, remember, there's not only one T model, there's many of them, all depending on your sample size. So if you remember, we were looking at 40 fish in our sample. That's 39 degrees of freedom. Easy math to do in your head. And that will give us our T-star, so we know how much to go up and down by. In this case, 2.0227. So, I mean, honestly, guys, it's really not that difficult. There's not a ton of extra stuff going on here. All you have to understand is it's the same process we learned earlier with confidence intervals. The idea is very simple. We're trying to find a mean that is in a sampling distribution. And it's in the center, right? That's where the true mean is. And we're just going to, put our confidence that our sample mean is pretty close to it. Hence, when we build an interval, we'll capture it. But that sampling distribution is not necessarily going to be normal because we're using S in place of sigma. It's going to be a T model, which is kind of very normal in a lot of ways. Nothing whole really changes with it other than we have to use a T-star because it is a T model. I mean, it's really very simple. All right, so if you're asked to actually build a T interval, you got to follow 4 steps. And these 4 steps should sound very familiar. Step 1, name the interval and what you're finding. I'm going to do a 1 sample T interval to find the population mean length of all largemouth bass fish in Lake Erie. Check the conditions for a T distribution. Same conditions for a normal model as well, right? Got to be random to avoid bias. Actually, give me 1 second. In the next slide, we're actually going to go over those conditions real quick, but you're going to recognize all of them. And then you got to build the interval. This is the easy part. X bar and S you're going to have. Sample size, well, you're going to know as well. And then your T-star, you're just going to use invert T. And then don't forget to interpret the interval saying you're 95% confident that the true mean population or the population mean of largemouth bass fish is in this interval. Okay, so let's just quickly go over those conditions and then we're going to look at an example here. All right, the sample must be selected randomly to avoid bias. The sample must be less than 10% of the population to assume independence. Come on, we've heard those 2 conditions for how long now? Now, the third condition is the only one that's a little bit new, right? Okay, the sample must be big enough to use the T distribution, right? Usually we say normal model, but now it's the T distribution, the T model. All right, to be big enough to use the T model, there's actually 3 things. A, if you, for whatever reason, already know your population is normal, then it's always safe to use the T model, no matter what your sample size is. Or, if your sample size is 30 or larger, the central limit theorem says the T model is always safe to use. And lastly, if your population is unknown and the sample is less than 30, then all you got to do is check your data, actually look at a graph, a histogram of your data, and make sure that it's free from any major skewness and outliers. Now remember why this is. All right, in the intro video, we talked about the fact that the shape of a sample should reflect the population shape. Well, we don't know what the population looks like, right? It says of an unknown population. But if our sample looks roughly symmetric, it doesn't be perfect by any means, just no major skewness, no major outliers. So maybe, we see a histogram and it kind of looks like this, right? Well, it's certainly not perfectly normal, but I don't see any major outliers. I don't see like a little hump way over here, or I don't see any major skewness. So as long as our sample looks roughly normal, then we would only assume that the population it came from is also roughly normal. So that's why we could still be okay to proceed even with a small sample size and an unknown population. All you got to do is make sure that your sample, your data is fairly good. And we're actually going to take a look at an example that we actually have to do that. All right, so this is it for the explaining video. I've explained everything there is to do. In the next video, we're going to actually look at 2 really good examples that put all this to use. And you know what, guys? At the end of the day, some kids really struggle to quite understand this T model and stuff forth. It's, I don't want you to say not to understand it. I hope you understand it. I hope you go back and watch the video if you need to. It's really not that difficult. But at the end of the day, when you do the problems, if you understand you need a T-star instead of a Z-star, it's really not that difficult at all. You'll see that the problems go very, very quickly. All right, so check out the example videos next.